Welcome to SS2 Computer Science, Term 3, Week 5. Searching is one of the most fundamental operations in computing, finding whether a specific item exists in a dataset, and if so, where it is located. Every day, billions of searches happen. Google searches the web, databases search tables, a program checks if a username exists. Today we study two core searching algorithms, linear search and binary search. By the end of this lesson, you will trace and implement both algorithms, analyze their time complexities, understand when to use each, and answer WAEC questions on searching algorithms. Let us begin. What is linear search? Linear search, also called sequential search, is the simplest searching algorithm. It works by checking each element of the array one by one, from the beginning to the end, until the target is found or the entire array has been checked. Algorithm, linear search, A. Target for I from 0 to length, A, 1, if A equals target, return I, found at index I, return -1, not found. Python code, def linear_search, AR, target for I in range, len, AR, if AR equals target, return I, return -1. Trace, find target equals 25 in A equals, I equals 0, A equals 64, 64 is not equal to 25, continue, I equals 1, A equals 34, 34 is not equal to 25, continue, I equals 2, A equals 25, 25 equals 25, return 2, found at index 2. Trace, find target equals 100 in A equals, check all elements, none equals 100, return -1, not found. Time complexity, best case, O1, target is the first element. Worst case, O(n), target is the last element, or not in the array, must check all n elements. Average case, O(n), on average, check n/2 elements. Space complexity, O1, no extra memory needed. Key property, linear search does not require the array to be sorted. It works on any array regardless of order. When to use linear search, the array is unsorted. The array is small. You need to find all occurrences, not just the first. You cannot sort the data, e.g. it changes frequently. You are searching a linked list, binary search requires random access. What is binary search? Binary search is a much faster searching algorithm, but it only works on sorted arrays. The key idea, since the array is sorted, we can eliminate half the remaining elements with each comparison. Binary search repeatedly halves the search space. Algorithm, binary search, A, target low equals 0, high equals length, A, 1, while low equals high, mid equals, low plus high, //2, if A equals target, return mid, found, L if A target, low equals mid plus 1, target must be in right half, else, high equals mid, 1, target must be in left half, return -1, not found. Python code, def binary_search, AR, target low, high equals 0, len, AR, 1, while low equals high, mid equals, low plus high, //2, if AR equals target, return mid, L if AR target, low equals mid plus 1, else, high equals mid, 1, return -1. Detailed trace, find target equals 25 in sorted A equals, low equals 0, high equals 4, iteration 1, mid equals, 0 plus 4, //2 equals 2, A equals 25, 25 equals 25, return 2, found in one step. Another trace, find target equals 34 in sorted A equals, low equals 0, high equals 4, iteration 1, mid equals 2, A equals 25, 25 less than 34, low equals 3, iteration 2, mid equals, 3 plus 4, //2 equals 3, A equals 34, 34 equals 34, return 3, found. Find target equals 1, not in array, in A equals, low equals 0, high equals 4, iteration 1, mid equals 2, a equals 25, 25 greater than 1, high equals 1, iteration 2, mid equals 0, a equals 12, 12 greater than 1, high equals -1, low 0, high -1 loop ends, return -1, not found. Time complexity, all cases, O log n, with each step, we have the search space, for 1 million elements, binary search needs at most log 2, or 1 million, is almost equal to 20 steps, linear search needs up to 1 million steps. Space complexity, O1, for iterative, O log n, for recursive, call stack. The requirement, binary search requires a sorted array. If the array is unsorted, sort it first, but sorting costs O n log n, so binary search is only worth it if you search many times. Direct comparison of linear versus binary search, requirement, linear, any array, binary, sorted array only. Time best, linear, O1, binary, O1. Time worst, linear, O n, binary, O log n. Time average, linear, O n, binary, O log n. Space, both O1, iterative. Data type, linear, any arrays, linked lists, binary, random access required, arrays, not linked list. Practical example to feel the difference, searching a phone book with 10 million names, linear search, average 5 million comparisons. Binary search, at most log 2 for 10 million, is almost equal to 23 comparisons. This is why binary search is the algorithm behind every dictionary, database index, and sorted search tool. Recursive binary search can also be written recursively, def binary _search _recursive, AR, target, low, high if low, high, return -1, base case, not found, mid equals, low plus high, //2, if AR equals target, return mid, L if AR target, return binary _search _recursive, AR, target, mid +1, high, else, return binary _search _recursive, AR, target, low, mid, 1. The recursion depth is O log n, space, O log n for the call stack. Other searching algorithms, hash table lookup, O1 average, fastest possible search, uses a hash function, used in Python dictionaries. Binary search tree, BST, a tree structure where each node's left subtree has smaller values and right subtree has larger values, search, O log n, an average, balanced tree. These are advanced topics. Binary search is the key algorithm for WAEC. Real-world applications of searching algorithms, linear search, checking if an email address exists in an unsorted mailing list, finding a record in a small database, sequential scan through an unsorted dataset. Binary search, dictionary/thesaurus lookup, phone directory search, looking up a product in a sorted product catalog, finding a record in a database index, BECE, based on binary search, version control, Git bisect, uses binary search to find a commit that introduced a bug, game development, finding a value in a sorted high-score table. Applications in programming, Python's bisect module provides binary search for sorted lists. The in operator for lists uses linear search, for sets and dictionaries, it uses hash tables. WAEC examination focus, trace linear search step by step, show which element is checked at each step and whether it matches. Trace binary search step by step, show low, high, mid at each iteration and the decision made, or go left, go right, found. Compare, state that binary search is O log n, and linear search is O or n, binary search is faster for large sorted data. State the requirements for binary search, sorted array. Write pseudocode or Python code for both algorithms. Common error in tracing binary search, always calculate mid equals, low plus high, // using integer division, always update low or high correctly, low equals mid plus 1 or high equals mid, 1, the loop ends when low, high, not found. Key points, searching, finding whether an element exists in a dataset and its position. Linear search, check each element one by one from start to end, works on any array, sorted or unsorted, ORN, time, O1, space, best for small or unsorted arrays. Binary search, requires sorted array, repeatedly compare target with middle element, eliminate half the array with each comparison, or log n, time, dramatically faster than linear for large arrays, O1, space, iterative, or log n, space, recursive. Critical requirement, binary search only works on sorted data, verify this in WAEC questions. Comparison, for n equals 1, 0, 0, 0, 0, 0, 0, linear up to 1 million steps, binary at most 20 steps. Recursive versus iterative, both correct, iterative uses less space. Applications, linear, unsorted data, linked list, binary, sorted arrays, dictionaries, database indexes. WAEC, trace both algorithms step by step on given arrays, write pseudocode, state time complexity, state the requirements for binary search, compare the two algorithms, identify which to use for a given scenario.